everyone, October the 9th. Okay, we have another hard problem. Minimum number of operations to make array continuous. You are given an integer array nums. In one operation, you can replace any element in nums with any integer. Nums is considered continuous if both of the following conditions are fulfilled. All elements in nums are unique. Difference between the maximum element and the minimum element in the nums equal to nums. Yeah, it makes perfect sense. For example, this is as continuous, but this is not continuous. So it doesn't have to be ordered, right? All we want is for everybody to be unique. And we might as well sort it, right? We might as well sort it, so make things a little bit easier. Yeah, 2, 3, 4, 5. So we sort it, and we want the largest and the smallest, the difference between the two to be, okay. I mean, uniqueness can do counter, right? We can do counter for uniqueness. I mean, I think the maximum number of change, okay, you can always set one value, right? You can always set a minimum number of operations to make it continue. You can always set one value and then change everybody else. Right, so we can do O(n) squared. It will work. No matter what, it will work. But we don't want to do that. Maybe we can do, I don't know. Yeah, you sort it first, right? You sort the whole thing, and you sort it 1, 2, 3, 5, 6. Okay, you sort it, and you find out everybody is unique. Then you say, okay, we want to make it you can do it in one step. Oh, really? One step? Oh, you changed this. Oh, sorting is not. Oh my god. Yeah, you changed this to 4. Whew. Damn. Yeah, I don't. It's funny, huh? It's funny. All right. 10 to the 5th. If you wanted the DP, maybe it's DP, then the state has to be a single value, right? So it could be position. From certain position to the end. I want to say, okay. But the thing is, yeah, the thing is, like, if you have this 1, not 1, if we have 5, right? 1, 2, 3, 6. This, oh, change for 1. That's still true. I'll put 3 here. Put 5 here. If we don't sort initially, right? Then, there's no way for you to change this. You need to change 2. So we do sort them. The sort give you a kind of idea, right? Okay, so we'll sort them. Okay, we sort them, and then then we sort them. We know someone is smaller, and then bigger. Then again, we can kind of see, right? We want to find starting from here to the end what's the minimum number to make this the continuous. And then we can say to do that, we can either maintain this, right? If we want to maintain this, we want to see from this to the end. So if we want to maintain this, then this has to be 2, right? Regardless, this has to be 2. Or you can say, I want to maintain this. Yeah, I mean, the idea is at the end, one of them will definitely don't change, right? So the maximum change is the length minus 1. So for each one you don't change, I just want to know if a certain value does not change, how many others do we need to change, right? The position. This is their position. Okay. So what my idea is, if you give 2, 3, 4, 5, and then what you will find is their distance to the position is all 2, right? So we can do the distance to their position. So it's 1, 1, 1. This is 2, and this is 2. So that is the distance. Okay, that is the distance. And then what? Then we can say, okay, so we have all that. And we can say, if we want, so we want to decide what distance we want, right? That's what we want to decide. We want to decide on the distance. That's not. What we want to know is if we decide on a value to keep, and I have all the other values, then what we want to know is how many are missing, right? How many are not in what I already have. But how can I check this fast? Okay, so we pick some value as the smallest. That we can do. We pick some value as the smallest. Okay. Then, if we pick a value as the smallest, then we know the distance between that to their index. Then we try to find how many already have that. How do you find that? Exactly, how do you find that? If we pick the first one as the smallest, if we sort everything, pick the first one the smallest, right? Then everybody else but they can move around. That's the thing, they can move around. Right? They can move around. It's just the smaller ones, they cannot become bigger, but the big ones can become smaller. No. Still doesn't make sense, huh? Still doesn't make sense. If we pick the smallest, or we can, check difference between, okay, if we check the difference between them, whenever we have the thing is you can move things around. That's the really, complicated part. You can move things around. I'm gonna have to check the hint. I have no idea, no clue. Honestly, no clue. Oh, no, let me close the window. Yeah, there's a cat on the outside, and my cat is hissing at the cat on the outside. Don't think it's healthy. Oh my god, my cat's going to another window. How about this? We try to find a stretch, you know? We try to find a stretch that's already continuous, right? We sort everything and try to find a stretch that's already continuous. So we can do that in ON, and we can say, okay, we have this stretch, right, followed by this stretch, followed by this stretch, and then these are the stretch that you can use, all right? And then based on this stretch, based on each stretch, you can try to see how many changes do you need. So if you don't have any stretch, right, there's no stretch, then that's actually not true. I was going to say that's actually not true. But you can have no stretch, but you still, yeah, that's not true. My stretch does save you space, but that's not. All right, I need some hints. What type of hints can you give me? Binary search. Interesting. Okay. For every index, do a binary search. For every index, do a binary search to get the possible right end of the window and then calculate the possible answer. For every index, what do you mean for every index? So we sort it, and we say, given this value, but you don't know. You don't know if this is at that position, right? There's no guarantee. Yeah, like if you are here. Hold on, let me think. So it's sorted, okay? So for each index, basically for each index, we try to see how many changes we need. If we keep it at that position. So you're saying that at the end, it will definitely be like at least one value is going to be in the right position after we sort it. Well, after we sort it, we have the current order, right? And if we say some value would definitely be there, but in the final answer, that value does not necessarily to be in its current position. It may be in a different position, right? It may be in a different position. But that's not what we concern. What concern is the correct answer, right? The correct answer, the ones with the minimum change, okay? The one with the minimum change. The one with the minimum change. If you want to change everything, yeah, you might as well change front and change back. It's okay. It doesn't really matter. So you might as well just keep yourself at the current location. And the only case that you're worried about is if it's in the current position, like in the end, it might shift, right? It might shift. That you say, okay, if I have current value, but in the end, they'll be shifted. They'll be shifted. Okay? They'll be shifted. But shifted doesn't matter. Shifted. It doesn't matter. So we have the current, right? And it doesn't matter where they are. All I care about is well, I mean, it just depends on how many is smaller than me and how many is supposed to be bigger than me, right? I mean, it doesn't really matter. Current, we have so many smaller than me, but in the end, we can change them, right? You can change them. What we're saying is the current index, that value does not change. If that value does not change, and we change the previous values, or we change the later values, are we saying that we just keep it at that position, that we can always find an optimal by keeping it at that position, just without changing? Just keep it at that position. We can prove it, right? If we keep it that position, we say if we move it, it will give me a better result. If we move it, that means we definitely have to change something in the previous, because they have to, they're not supposed to be there, right? So we definitely have to change extra, right? Then if we don't move it, then we also change those, or maybe we don't have to change it. So that's actually, I think that's correct. No matter what, in the final answer, some value will be in its correct position. Some value will be, okay? I think that's correct. Because if you say, if it moved to a different location, that will give you smaller. And once you move a different location, you're guaranteed to change something, either on the left-hand side or right-hand side. But if you keep it at this position, you can also change front and back. But you can also have a possibility that they don't make change, and then that gives you a smaller chance. So yeah, so we say some value, right? Some value definitely. Well, if you set it to be correct, it's gonna be in this position. Okay. So okay, for an index, we say okay, this value is in the correct position, and by that, and at that position, you know what is in front, you know what is behind. Right? You know it. You simply just know it. But then comes the issue of how do we know how many values we need to change? Right? How many values we need to change? Well, you can definitely calculate the largest you need. Right? And you can actually check if that value is, if that largest value is already in it, already in this, right? Or you can check if this is in this position and the largest of values are already there. Yeah, there could be repeats. Okay, it could be repeats. So that's really not convincing. Right? It can be repeats. And if you have repeats, those has to be changed as well. But then how do I know? Find the largest. You can do a set to see. You know, if the largest exists, or you can actually find where the largest exists, right? If you find out where the largest exists, you can count. Yeah, if you find out if you let's locate 3 is the correct one, and you find out the largest you need is 5, and then you binary search, you locate 5 as in this position, right? Now 5 is this position. That means anything to the right need to be changed. No question asked, right? Anything to the right need to be changed. Right? Anything to the right need to be changed. Yeah. But what about things in between? Well, the things in between, yeah, let's just say we have a longer, right? So you have the largest, you find the largest, it's somewhere. And the ones in between are smaller, right? They're smaller. And they should all be there, right? They should all be there. Huh. If I know the total number of unique values in between these two, the unique values in between these two, or even simpler, total number of if I know the number of unique values between so I have a current one, and I know the largest one, and then I binary search. I know where the largest one's supposed to be. Okay, so I can put it in the index. So in between these index are the values smaller. Okay, then I need to know how many uniques are in this, because all the uniques in this we don't have to swap. We only need to swap out the duplicated one. But yeah, the question is, how do we know? How do we know the number of uniques in between a range? In between a range. I do not know. But can we know that? I can know the number of counts. I know the number of elements in between them. That I know. Okay? I know the number of elements in between them. That all I need to know is the number of uniques between them. Which means I do know. If I do a counter, right? If I do a counter on all of them, and I create an array of all the keys, and I sort the keys, then the number of uniques between the two is gonna be that. So I know the number of values in between them. So with that, I know how many numbers I need to change. Or to put it in yet another way, given a value in its current position, I can find the largest needed, right? And once I find the largest needed, I can count the uniques in between these two. And those are the numbers, those are the elements we don't have to change. Then we can find the smallest, right? The same thing, we find the smallest, and we find the number between them, and that's the values we don't have to change, the number we don't have to change. That sounds doable. That actually sounds doable, right? You sort it. So I'll do that. I'll do a counter, and I'll sort. So basically two, right? We have two things to sort. One is the original array. Huh. Do you even need the original array in this case? Why don't you just do a unique, the array of uniques, right? If you do the array of uniques, right, and then given a current value, and yeah, but you don't know. So we sort, yeah, we have to have two, because I need to go through the original array to say, okay, you're gonna be in that position, right? You're gonna be in that position, so I can compute the minimum, I can compute the maximum, and then I can binary search in the unique arrays, right? You can binary search the unique array. So in the unique array after I binary search, I get the index, right? We get the index, the index of where it's supposed to be. And we can decide how many uniques are between them. So those are the ones we don't have to change. So we get that, and we have the total minus this is the number we need to change. I think I can do this in Java. Will not be trivial, but I think it's possible. Let's give this a shot. Right, here's this thing. So first of all, I need to say, I forgot, how do you sort? Java sort array. Arrays.sort. I think that's the one. Yeah, I think I can call arrays.sort nums. Perfect. Then I need to say a map. Yeah, I like to do map. Integer. Okay. Counter new hash map for int n of nums. Oh, I don't have to. I just need a set. How do we do it? Java set from array. Convert an array to set. Okay. So I say set integer nums set equals to new hash set arrays dot as list nums. Okay, always give me this error. That's why I don't like it. Add amount static import. That doesn't make any sense. Oh, I think I should use this. Because this is a small int, I need a big int. That's fine. We'll do this. For int n of nums numset.add n. Because you'll have to go through a loop no matter what. now I have a set. Then I want to sort a set, or Java set to array. Do we just go to array? Set.toArray. I can say integer, right? Integer uniques nums set.toArray. New integer 0. Okay, then arrays dot sort uniques. Okay, so that's the preparation. Then we're gonna do is for int I equal to 0, I smaller than nums dot length I plus plus for each one. Okay, for each one we can say int. We can put int outside the min int max. Okay, then min shall equal to nums I, whatever it is, minus I. Okay, and int and max shall equal to nums I plus what? Plus nums dot length minus I. So if I is n minus 1, right, then length n minus 1. I think you should minus 1. Right? If we do that, we can actually try. So if you are here, you're 0. Length is 1, 2, 3, 4, 5. Length is 6. Length is 5, right? So 1 plus 5 minus 1. Yes, 5 minus 1. So that is the maximum. Then you need to binary search in the uniques. Okay, binary search in uniques. So we can say min index and max index. Okay, and we say min index is equal to collections dot binary search. We'll search the uniques, right? What's this signature? Or maybe we can do arrays instead of the collection. I think arrays. It doesn't have. It does has. Okay, so what do we need? Binary search. Okay, so uniques and the min. Okay. Now, if it finds it, and in fact, once it finds it, it will give you the index, or it will be negative, right? The negative, so you need to do negative. Oh, I forgot. Do we still have? Yes, binary search. Insertion point. So we'll do negative this, negative whatever it give you, or this plus 1, negative this one plus 1, right? That will be where it's supposed to insert, right? So for minimum, so I'll say we need to have interest integer dot max value. Okay, so when we have the index, what we want to know is the number int no change small, okay, and no change big. So we want to know no change small, right? Then index, if min index is smaller than 0, min index equal to we'll do min index plus 1, right? So plus 1, we remove this thing and we take the negative of this. So that is where it's going to be inserted. So now we have the min index will be pointing to either the minimum value or we're pointing to where it shall be inserted, which is the value, the smallest value that's larger than the min, right? Then what we need to know is, gosh, I need to know also the index. I need to know the index of the current value as well, because I'm doing the unique search, right? I need to know that. Shoot. How do I know that? I can set up another hash map to do that. Okay, I can do that, or I do another binary search. Okay, let's just set a new hash map. We can call it map integer val to index. Okay, and for int I equal to 0, I smaller than unique star length I plus plus. What we do is val to index dot put uniques I. That's that. That's just sort original nums, sort unique nums. This is produce a mapping between unique num and its index. Okay, and this is go through each num in nums and treat it and consider that it is at the correct position. Find out how many moves needed to convert the entire nums array to continuous, right? So now we have the val to index. Then we can say no change small shall equal to val to index dot get nums I, right? Dot get nums I, that's the index, minus min index. Okay, because I want to know how many is in between them, but not including the current value. So if we would say 2, 3, 4, 4 minus 2 is 2, so that's that. Okay, yeah, so handle the minimum needed when nums I does not change. So similarly, we need to handle the max needed when nums I does not change. Okay. Oh, might as well just do this later. Oh shoot. Okay. So we do the max, and when the max index is arrays dot binary search uniques max. Same thing, if max index is smaller than 0, max index will be minus max index plus 1. So that is going to point to either the insertion point, which is actually to the right, to the right of where you want, because this is pointing to the value. This is pointing to the value that's smaller or larger than what we need. Okay, so in this case, we try actually minus 1 more time, and then we say no change big shall equal to max index, right, minus val to index dot get nums I. So again, say 2, 3, 4. If 2 points to the core index, 4 is the one, right? Then if you do 4 minus 2 is 2, right? 2 does not need to change. So res, now we can say equal to mass dot minimum res the total number nums dot length, okay, total number minus no change small minus no change big minus 1. That's the current value. So we do that, and once we handle everything, we will return the rest. Okay, we will give this a little shot. Just run this. I give you 0. Let's do all of them. Give you that. Let's do I don't know, just throw in some value out there. Okay, we have, I think that's the last test cases I want to do. Oh, okay, some repeats and a 1. I think this might be right. I don't have as much imagination. I was very confident. Thought I got it. Thought I got it. Main operations. Okay. I don't know. We need a debug. Okay, that's nums. What's my unique? Yeah, his unique is good. Ugh. So output 6, expected 5, change 5 values. So if it's 7, 8, 9, 10, 11, 12, 13, 14, it should be 14. Let's go F8. Minimum is 7 and 7. Main index is 0. Okay, so no change, small is 0. That's correct. Max should be 14. Max is 14, right? Max is 14. So if max is 14, we have 1, right? Max 14, then max index I am expected to be 1. Yes. So with 1 minus this, then no change big shall be 1. No change big is 1. So the total no change is 1 plus 0 plus 1 is 2. So we need to change 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 2 is 6. Right? 7, 8, 9, 10, 11, 12, 13, 14. So that's Rest now becomes 6. Okay. Now we'll do 10, right? Then we should have 9, 11, 12, 13, 14, 15, 16. That's 5. Okay, so minimum is 9. Min index is 1, so that's 0. No change is 0. Maximum shall be 10 plus 1, 2, 3. It shall be 11, 12, 13, 14, 15, 16. Max is 16. And I do binary search. Oh, shoot. No shoot. It will find that the max is 2. Right? That's 2. Which I don't make any change. Then, no big changes. 1. No big change is 1. No small change is 0. Oh, yeah, that's right. 10. Oh yeah, 9, 11, 12, 13, 14, 15, 16. So we have 16 and 10, but that's it. Oh, that's still 8. Oh, that's still 6. All right. Okay, if we do 16, 17, 18, 19, 20, 21, nothing. If we go 22, but if we put 22, 21, 20, 19, right? 21, 22, 23, 24. But 34 and 35. How would you do 5? One, two, three, four, five, 6, 7, 8. 8 minus 5, which means we can keep 3. We can keep 3. $28, $29, $30, $31, $32, $33, $34, $35. And your theory is wrong. It basically says your theory is wrong. Oh, God. So, are we saying that we put everybody to try for it to be the smallest? Is that what we're saying? For everyone, we try it to be the smallest. I don't know. So each one we try to be the small. Like why? Why would that work? We try to make it the smallest. Yeah, I think this is basically what we're trying to say. Like we need to try to see every value. We will need to put it at the smallest. We try to make it the smallest. But like why? In this case, you put 16 as the smallest. You will include. It actually does make sense, right? Because you're looking at some value, okay, and your goal is to include as many value larger than you as possible. Okay, if you do that, then you can, yeah, as many value larger than you as possible. Then yes, you put this as the smallest, and then you would do the same thing. Perfect, it will work. But why don't we consider, the smallest? You try to include as many values smaller than you as possible. Well, if you want to include as many values smaller than you as possible, isn't that equivalent to, when you consider those smaller values, you try to include as many larger values as possible? Does that make sense for you? Yeah, I think that it does. It does make sense. And then if we do that, why do we still need the original nums? All we need is the unique ones, right? That's all we need. The unique ones. We need the unique ones. I will go through the unique ones. So we go through the unique ones, okay? And yeah, we'll go through the unique ones. So hold a second, let's cancel this. So here is a new idea, okay? I will go through the unique ones. And we don't handle the minimum. We try to find the maximum. And the maximum is going to be this just -1. Because we consider the current value is the smallest. Alright? That is not nums, that's going to be uniques. We consider the current one as the smallest, and then I need to add nums $length -1. That's the max. Then we do this, then we do this, then we can find. We don't need a val to index. I don't think that's necessary because I is my index. I is the current index, right? It's because I am at I. So when you do that, then we don't do this, and then we do that. So we give this a shot, see what comes out. 5, right? We get 5. So with that, we can say I do not need this. I do need the unique num, so I need to do that. Do that, do that, do that. I don't need this. Okay, I need to just try this, try this and see if it works. Dude, I think this might actually be the answer. So it's slightly different than the original idea. So we need to go through each nums in uniques, right? Consider that it is the smallest, right? It is the smallest in the final continuous array. Then no, let me put it this way. Go through each nums in uniques and consider and try to include as many nums, as many elements larger than it in the final continuous array. To do so, we must set the current num as the smallest in the continuous array. Then we can find the largest, find the max needed, and use binary search to count the number of unique values in between any values already existing, right? Already existing in the nums. These are the values that do not need to be changed. Yeah, and we check. This also gives us the minimum number of values to change for each unique nums serving as the min of the final continuous array. Now we only have to consider the current num as min in contrast to as max, because the purpose of considering the current num as max is to include as many elements smaller than the current num, right, in the final continuous array. Now this is equivalent. This is equivalent to previous rounds on those smaller elements, right? Trying to include the current num, right? Trying to include the current num. I don't know if it makes sense. It makes sense to me. When they try to include the current num in the final continuous array. Thus, we don't have to do this operation for both min and max. So that's why this is not needed. This is not needed. We probably don't even need these, because what we can do is we do that, and we simply do this. Right? Minus this. Okay. Okay, one more time. Looks good. Looks good. Yeah, a hint helps. (2009). Hint. The hint helps by I mean, the hint doesn't really, yeah, the hint helps pointing me on the right direction. The explanation is provided in the comments below. On login. On login. Okay. Now it's time to check the official solution. Binary search. Unique. Binary search. I think it's exactly the same. Left, right, binary search, count. Sliding window. Holy crap. How do you do sliding window? Oh. Yeah, if it's smaller, just keep going until we hit. And now we keep going. Yep. I think I know what this one is doing. I think it's complaining about yesterday's problem. Or something of the sort. Alright, let's try that. Yes, I can understand this second solution. Approach number 2. The second approach from the official solution, where we use sliding window to find the index in uniques that points to a value that is smaller or equal to the desired max. Okay, max, yeah, I want that. Max index, I want that. It's the same thing. Get a max. So this is slightly different. Ooh, and this one is actually moving. This one is moving forward. Right, we can say while max index is smaller than uniques dot length. If and uniques max index is smaller than smaller equal to, okay, smaller equal to max. If this is smaller and then this is, and then we just plus plus. Okay, so while this, then when we come out, max index will pointing to will be pointing to the value, the smallest value that's bigger than your max. Okay, then we don't need this, absolutely don't need this, and we don't need to -1 anymore. Max index. Yeah. We might as well. I mean, it's okay. Max index plus plus. All right. Let's try this one first. 5. That was good. Yeah. Ooh, sliding window. Sliding window. Very good. We like sliding window. Yeah, sliding window and a binary search sometimes can, interchange. Okay, that'll be it. I don't want to do another one. Let's just call it. I'll see you guys tomorrow. Adios.